How did you guess?
Okay, I guess we better start today. I still see a few empty chairs this morning. It must be the day that problem 4 is due. Problem 4 is the one that we're trying to solve. Has anybody solved it? What? No? No? Amy? No? Marianne? No? Kathy? No? Andy? Dimitri? Pang? John? Did you solve it? No?
Ramsey?
Ramsey? Don?
That's one of the cameramen here.
Okay. Well, look, don't tell me that I finally stumped the best minds in the world on a problem here. Do we have any partial results? Do we have any? I mean, there's the total result, which says that you know exactly what that you need 3 to the n minus something like 2 or something as a minimum number of configurations. But does anybody have any partial results saying if you're going to get a better construction than that, then it has to be of a certain restricted form or something like that?
I think Neil might have, but he's not here, so.
Neil might have, but he's not here. Okay. What do you think, Neil? How do you think Neil did it?
Neil, so I don't know. He was talking to Mike about it the other day.
They were working the other night and they thought they had a proof and then found a bug in it.
Oh well. It's not for Neil.
I don't know if they've gotten anywhere since then.
Yeah, I think Neil decided he should work on the portrait at this point.
Yeah, well, there is that.
Yes.
I understand that you have an absolute deadline of Thursday, and this deadline was a little less firm. Okay, so now let's see. Well, I should try to figure out how to play it then the rest of this morning. At the end of the hour, you're supposed to do class evaluation, and so I can't just blow it completely. I mean, although when you fill out these forms of evaluation, please remember all the other great times we've had, just in case I do blow it this morning. Okay. Well, I've got. So Roger, you don't have any partial results or anything?
I didn't get anywhere.
Didn't get anywhere. That's interesting. Okay. Well, I mean, sometimes, we gotta face the prospect of failure. I don't know. Maybe you guys are better at it than I am at giving up a problem. Maybe. One of the things that happens to me occasionally is that that I just can't get over the curiosity I have. I just have to know whether something is true or false, and I forget to sleep, eat, and all these other things, which is then bad for my, for my health, etc. It's almost as bad as time sharing has been for my health. I've had to stay up late to use computers when I couldn't get good cycles during the day and stuff. But sometimes, well, I think that there were at least 5 times in my life when I worked very hard on a problem and finally decided, yes, I'm not going to solve it. I've got to give it up, and I'll never get it. And 3 times, I think, of those 5, an idea came to me an hour later, but I wouldn't have probably gotten that idea if I had kept grinding on it. But I finally decided that I was, that I was going to, that there was no way I was going to go on. I had to go on with the rest of my life and so on. And I was prepared to give it up. And so several problems I have given up on and never solved. For example, the P equals NP problem. And once I thought I had a 4-page proof of that, and I got to the point where I had written up the paper proving that P was unequal to NP, and it was time to write QED, and then I realized I hadn't proved anything at all. I thought I was completely done, and all I had to do was write, and that proves the theorem. And then I realized that that my whole construction made no sense. So sometimes I just deluded myself, and then so there are times when I had to come to terms with the fact that I wasn't going to prove that P was unequal to NP, and similarly for a few other things about deterministic languages and things like that. But other times. Somehow it seems that our subconscious will go to work on a problem after after we're conscious, after we're done with it consciously, and all of a sudden, middle of the night or something, you'll say, "Wait a minute, doesn't this fit?" And then all of a sudden, the thing crashed. I have one. I think still that we ought to add some footnotes to what we did on Thursday, because there are more powerful results than what we did last Thursday, and this will lead somewhere, if not to the final solution. Then at least this is there's more to be said, I think, than we did before. So I better mention that today. And then if I run out of things to say, and if you run out of things to comment on, then I could talk about halftone fonts or something like that related to portraits. All right, so let's see now. Last week we had a construction that showed pretty good grounds for believing that if we had 3 two-state devices in the system, we were going to have trouble completing it. Now I wanted to examine that a little bit further. We started out on that time saying there exists a good cycle, and therefore we got this construction of the alphas and betas that had to march along. Now, I really haven't worked this out at all, but I've got some ideas that I think should be mentioned, and maybe you can see also how it works. In the first place, instead of saying that there exists a good cycle, we might state, if you start with any arbitrary configuration, then if we follow any continuation of moves from that configuration, we eventually get to a good cycle. So that's a slightly more powerful statement. And in fact, we could just say, just take the leftmost sequence of moves, for example. Suppose that if you have a configuration and several processors can move, let's just move the one that the leftmost processor, say, in a pattern, and then see what, and that defines a unique that defines a deterministic sequence from a configuration. Furthermore, even if we take a partial, if we have a partial, some part of a configuration in which there's at least one baton, at least one thing able to move, then we can look at what is the leftmost consequence of that configuration. So we can say, for example, if I have a string, if I have part of a configuration and say it's preceded by a zero-state 2 processor and some zero-state processor at the right, and I have some configuration alpha here, either alpha is stuck, or it can eventually, or anyway, it defines a leftmost sequence of states. Of moves. So if any of the processors in alpha can move at all, let's move the leftmost one. Let's forget about these zeros here. Let's not move them in any case. And I'll keep on moving this until I get to alpha bar, which is the first time in which it can't move anymore. Okay, there's got to be some. This is a well-defined mapping from alpha to alpha bar for any processor. And any 2 things in front of it, any assumed states before and after, saying always move the leftmost thing you can in alpha and see what the corresponding alpha bar is. So now that is some mapping from configurations to configurations that might help out in this process. So in other words, we've got to know more than we did last Thursday, and so the way to do it is to find a way to have a notation for the things that we're coming up with. I see Arif has just arrived. Have you solved the problem? You haven't solved it? Do you have partial result?
No.
No? Okay. Well, maybe Emil will show up in a minute. Okay. Now, so let's look at this idea then. We could I don't know, this alpha bar might be called alpha of 0, 0 or something. Have some notation for it. For any configuration and certain neighboring states, we have a mapping as to what it would go to if we made all the moves that we could whenever there's a choice of more than one. Choose the leftmost, say. Now, then we might be. Then there's a possible chance of getting counterexamples with that. Okay, now let's look at the kind of things we had last time. But I'm going to write out explicitly alpha 0, 0, beta 0, and for the time being, I want to simplify the setup over what we had last time, because again, another idea for working on a problem we can't solve is to say, well, let's add an assumption or simplify something and see if we can't solve a simpler problem, and then if we can't even solve a simpler problem, then we're really in trouble. If we can solve a simpler problem, at least we have some idea for what doesn't work on the more complicated problem as well as what might work on the more complicated problem. So we've got to simplify it down a little bit. So I'm going to simplify it down to the point where I have two non-empty patterns instead of 3. So I'll assume that I have two-state processors, and then I have between them some undetermined number of processors, at least one, and some undetermined number of processors, and their initial configuration is alpha 0, beta 0. Let me actually give myself a little room here. And I'll say that we start out in this situation. Now, let's see, where was I? So instead of 3, I put 2, and I'm putting in the zeros explicitly. The other assumption I want to make is that in all reasonable things I want to look at, the motion through a two-state processor will always be to the right, and so I'm going to assume that I don't back up once I've gone through. So the first move was to here in our assumed good cycle, and I'm going to assume that when I get done, I get to. I haven't changed this 1 back to a 0 again, but it's still sitting at 1. Now, this is an assumption that I can't make in general. I have to verify it later on, but I'm going to assume that as first of all, I'm going to go back to the idea then of last week that we have a good cycle and that the baton is moving, but I'm going to say that once the two-state processor passes the baton to the right, he never gets the baton again until it comes to him again from the left. That's the assumption I'm going to make, and see if that if I can construct if I can show at least that it's impossible to do it under these circumstances. If we can show that, then we say, well, okay, maybe then the only possible constructions are ones in which the baton gets passed back to the two-state processor, and then we can see if that helps us any. But first, let's consider that simpler case. Now that means that the reason that this has some effect because it gives a parity condition. 0 always goes to 1, and then on the next lap 1 goes back to 0, and on the next lap 0 to 1 again. This one then we'll finally get to a situation where alpha 0 has gone to alpha 1, and then the next move is alpha 1, 1, beta 0. Now, and this pattern continues. before I go further than this, I wanted to mention we could also go to the notation I had a minute ago, saying if I have a 1 alpha 0 0, that this is, and then I move the leftmost thing in alpha 0 that I can. In general, this will take me to a alpha 1. This will take me to a 1 alpha 1 0, which is the first time that there's no more moves left. At this point, we get to this. So in general, we can assume without any, we know without any assumptions that this state that would lead us to that if we start with this configuration, we're going to have to get to this configuration sooner or later. Let me see. There's a sequence of moves that takes us to this configuration, after which somebody else has to move. Alpha 1 is now stuck. Alpha 1 is dead when it's preceded by 1 and followed by 0. Now at this point, then somebody else has to move. And in our good cycle, if this was really a good cycle, beta 0 was stuck when preceded by 0 and followed by 0. Therefore, beta 0 can't move, alpha 1 can't move. So it's got to be either this 1 moves or this 0 moves. All right. Now it comes time to make my assumption that the baton is always going to go to the right, and so it's going to be this one that moves. That's what's going to force it to go in here. The other possibility that we go from here to 0, alpha 1 0 is something else that I would explore later. But right now I want to always consider the two-state ones always going to the right, if anything. All right. So at this point I get alpha 1. 1, okay, then what happens next, the same kind of a thing occurs. 1 beta 0 1 followed by a 1 is going to lead eventually to the first case where the betas can't move anymore, and that we'll call beta 1. And now, so beta 1 is dead, followed by a 1. Okay. I was thinking we're assuming that this was a good cycle, which also allows us to prove that to conclude that alpha 1 followed by 1 is dead. But in the more general case, I guess we can't do that. Okay, then this will lead us to then, by the same argument, 0 alpha 1 1 beta 1, and that will go then to 0 alpha 2 1 beta 1. 0 alpha 2 0 beta 1, and so on. Beta 2 1 alpha 2 0 beta 2, and up, and then this will eventually have to get into a cycle. It'll be eventually cyclic. So the alphas will be equal, and the subscripts on the alphas and betas will be modulo something or other. I want to go up one from the beginning position just to see what it's like. So that would be corresponding to this one. So there will be a 0 alpha 0 0 beta minus 1 here up above in the environment of that thing, or a minus 1 meaning k minus 1, where k is the period length, or p minus 1. Anyway, this is the way it'll look. Now, in this situation, then, which we know these alphas and betas are going to exist, and if we assume this baton always to the right in the two-state processors, we also have this kind of a pattern where the alphas have the alphas have different subscripts keeping on growing, but I haven't done any more. Now, what do we know about these alphas? And we know that 0 alpha sub 2k0 is dead, and 0 alpha sub 2k1 is dead. For example, 0 alpha 0 is dead because it didn't have the baton, it didn't move from here to here, and 0 alpha 0, 1 is dead because it didn't move from here to here. With the and on the other hand, in the odd case, 1 alpha 2k plus 1 0 and 1 alpha 2k plus 1 1 are dead. Now, what about the other one then? So 1 alpha 2k, like 1 alpha 0 0, this leads to 1 alpha 1 0, 1 alpha 2k plus 1 0, and 1 alpha sub 2k 1 is unknown. You don't know what happens to that one, but it can well, yeah, we don't, almost anything can be happen there. We haven't got, that hasn't arisen in the cycle here. Similarly here we got 0 alpha 2k plus 1. So 0 alpha 1 1 leads to 0 alpha 2k plus 2 1, and 0 alpha 2k plus 1 0 is unknown. Yeah, John?
I don't quite see what you can get by having 4 processors, because there's obviously the case where the alpha and beta are 2-state processors.
Yeah, that's right. There's a case when which will actually arise that works with 2-state processors. That's correct. But somehow we'll have to. That'll force us maybe into a sort of. There's only one way that can work. And so that'll force us into a higher level consequence of this, which then would have to be true if we went to 4. For example, if there were really 6, we could absorb it and call it 2 and 4, and then we know something about these 4, maybe. And similarly, we could call it 4 and 2, and then we know something about these 4, and then we might be able to combine that too. I mean, I have no idea, but first of all, I wanted to see what we can prove about it from this level. But your point is very well taken. That I'm not going to show it's impossible. I'm not going to definitely come up with there's at least one way out of this mess, isn't there? And it must be because of these question marks here. In fact, in the case of 16 things. Yeah. Okay. Now. One of the things that might be true is that the period has to be fairly short, for example, in that case. I mean, maybe the period, let's call this P for period. Maybe the period has to be 4 or 8 or something. But let's try to find as many consequences as we can of these primitive axioms. We have more things to check. Now let's see. One of the things we can conclude is that P is even. Why do you see why that is?
Well, you just compare what happens with a 2k and a 2k plus 1.
Yeah, because if P were odd, then alpha 2k would also have to equal alpha sub 2j plus 1 for some j, because there would be, the evens and odds would get mixed up, and we do have a case that this one is dead and this one is alive. So that's a contradiction. So we know that P is even. Small theorem. Okay, we can take anything at this point. Okay, now the next thing is let's look at what happens if we start out with 0 alpha. I'm sorry, 1 alpha 2k 0 beta 2j minus 1, where j and k might not be equal. Well, in this is a situation like we had on the board on Thursday, where we wanted to try to get a counterexample. And this is a case where we have two things. I didn't write the laws for betas. The laws for the betas are exactly the same as the laws for the alphas, except the rightmost bit is complemented. And so, for example, 1 beta 0 1 is what we know. Here's 1 beta 0 1 is what we know goes to the next case. It's not 1 beta 0 0. So when you have a beta here, you have to complement the value on the right neighbor. It's too bad, but it's true.
Or decrement the subscript in the beta.
You say the even and odd are different on the beta? I don't think that's true.
Well, because
the zeros. It's going to be, for example, it's going to be 1 beta 2k1 goes to.
You're not considering this as just a substring of process. This is supposed to be the complete ring you've got on the board there. Okay.
Yeah.
Okay.
Yeah. This is a complete. This is followed by the next one. Yeah. Okay. So the one on the right has to complement its right input as far as the laws of that satisfies are concerned. So 0 followed by an odd beta followed by a 1 would use the same thing. 0 followed by an odd. Wait. It's interesting. 1 alpha 2k0 0 beta 2k. I'm seeing if this checks with my other notation. I'm confused here, sorry. 1 alpha k1 0. Okay, maybe I just wrote it down wrong. So if I have a 0 followed by an odd beta, then that followed by a 0, then I know what it happens. But here I really don't know what's going on this side, do I? Okay, well, so I don't know what's happening here. But I do know that this one can go to 1 alpha 2k plus 1 0 beta 2j minus 1. Now let's see. So at this point, okay, this differs from what I thought was true. At this point, the alpha 2k plus 1 is dead in between here. Beta 2j minus 1 preceded by 0 followed by a 1. I don't know what it'll do. But let's see, it is. Let me write out what I know about 0 beta 2k 2j minus 1 followed by 0 goes to 0 followed by goes to 0 beta 2j 0. Alpha 2 That's not the case I wanted to consider. we'll get into something like this in a minute, but let me go to this one. I think that's this one. This is the kind of thing that I really had in mind, I think, when I started out. I got 1 alpha 2k 0 goes into the next case. 0 followed, no, that's dead. Well, let's watch this one anyway, see what happens. This one will take us to this situation. Beta 2j preceded by 0 is dead. It falls into this pattern. And so this, we get here, and now this is dead, this is dead. So one of these two has to move at this point. Either the this one or this one has to move. So if, for example, this one moves, all right, well, we have either the 1 changes to a 0 or the 0 changes to a 1, or both can happen. But we can't have that neither happen, because then the whole thing would be dead. And even though this is dead, we can't have it in this problem. So we got to have. So let's suppose that this one changes next. That this one can change at this point. So say this one can change. Well, in that case, then we could. Then we can go to beta 2j plus 1. At which time this is dead again, and this one is still still dead. And so again, we're faced with the same situation. Either this one can change or this one can change. And suppose this one can change now. Well, in that case, we see that k and j will be stepping along just as if they were equal. And so that would give us a good a cycle that looks good. All right. Now, if this happens all the time for all values of k and j, that it always turns out that when there's a choice between these two, which one can move, it's always going to be the one that to the right of the guy that had just moved. The baton is always passing to the right. If it always happens like this for all k's and j's, then that gives us a fairly strong condition on our state diagram. So it gives us lots of good cycles for whatever p is. P is some even number. Suppose p is 20. Then it says we can start out at alpha 0, beta 0, or alpha 0, beta 2, alpha 0, beta 4, up to alpha 0, beta 18, and get a bunch of a whole bunch of consequences of what the states are on that thing. That's one possibility. What's the other possibility? The other possibility is that we would get, at least for some value of k and some value of j, we'd get to a situation where this one would now be followed by where this 0 is stuck, is dead when preceded by these when k is not equal to j. And in that case, this one would have to still be movable, and it would take us to 0, alpha 2k plus 1, 0, beta 2j. Okay, now, so now beta 2j is still dead in that point, but we've got now this is still stuck. This is still stuck. the only thing that can possibly have changed, see beta 2j followed by either 0 or 1 is dead. So, there's nothing we can do here. So the only thing that we could possibly do is go in this one. This is one of our unknown cases here.
No, I thought
No,
that,
Kathy?
if you look at you said beta 0 beta 2j 0 is stuck. That's
Yeah.
0 alpha 2j 0 is stuck. If you look at the
I'm
table on the
sorry,
left.
0?
No, if
What?
you go back and look at the table on the left, don't we have that at the top? You were using that to say that 0 beta 2j 0 is stuck. Actually, if you
Yeah.
that's for alpha, that rule though. Don't we have
Yeah. Well, it's complementing the right
Oh,
neighbor,
sorry.
but these but we have both cases.
to? Sure.
So it's actually, I use this case and this case instead of this case and this case.
Right,
Yeah.
okay.
But they're both dead. So, yeah, right. But I'm glad you're watching me, because I might make a mistake at any time. I haven't gone anywhere from here. Okay, so now, so at this point, we've got to move there. That's our only hope. And so this must go to something. We take the leftmost thing that can move at all times or something, and this must go to alpha 2k plus 1 bar, say, before it gets stuck. And okay, so let's see. In that case, now I've got an alpha 2k plus 1 bar that's stuck, and so one of these two zeros has to move again. All right, now let's see. If it looks to me as though the way to continue on hacking on this problem is something like this. I would try to find property. I would call this maybe alpha 2k plus 1 super 1 or something like this, because if I might be able to pursue this and go on to super 2 and super 3 but I would like to make a table that would say something like this for the alpha bars as well. So I have some kind of a mapping between these alphas, and I try to keep deriving properties like this as I go on. So I'll know something about alpha 2k plus 1 bar, and I'll know that there are certain pairs of k and j for which this two-state machine is stuck, and some pairs for which it isn't stuck. So there's some maybe number theoretic property, combinatorial properties of the j and k. When j and k are equal, we know that this one isn't stuck. So, but how discriminating is it going to be? In one case, you might think that this second processor here is just one processor and has lots of states, and then this one gets to look at all those states and decide when it's stuck and when it isn't. Arif pointed out last week that if we had two of these two processor things in a row, it looked like it was hopeless to get much information across. But that's sort of where we're confronting it here. Now,
one thing that you might be able to do to be able to make more headway, I mean, as long as you're going to assume that you're always passing the baton to the right, you might as well make another assumption, and that is that with these states that are question marks, you could assume that those are also stuck, because I mean, if you're looking at some setup where you've got sequence of good configuration.
This one can't be stuck.
What?
This one, it's got a baton at the left, I know, because it moves in this pattern. Well, I'm sorry, if the alpha is only one processor, it could be stuck. But if it isn't, if there's more than one processor in here, it can't be stuck. And so if I got more than, what? Oh, okay. Suppose there's two processors, so then one alpha 2K looks like one A, B, something. And in this case, it moves. And in this case, it's got the 1 over here or 0. It doesn't know yet, which it doesn't know yet that it's time to be stuck.
Okay.
How do I see it as one
So
alpha?
when n is large enough, at least, one of these is going to be more than 2. What, Ramsey?
Otherwise, from the starting state, 1 alpha 2, 2k, 1 alpha 2k plus 1, 1 alpha 2k, 1 alpha 2k plus 1. You could, or beta 2. Oh wait, no, never mind. I was going to say you couldn't move at all. So that's still.
Yeah, that's what I was thinking before. Is I mean,
Yeah, I want to get a contradiction, and we could get a but I can't assume that this one is dead, I'm afraid.
Yeah.
I can assume, however, that it dies out quickly or something like that. See, so let's, for example, okay, let's put a assumption on here that this goes to 1 alpha 2k plus 1 bar. I'll put 1 bar on and see if we can get 1, for example, that it goes to something like that, which is dead. That defines alpha 2k plus 1 bar. And now we try to get some rules of the game on the alpha bars as well as the alphas. And then and that might lead us to rules on the alpha bars and things like this. But this is a general idea when you're doing research on something and you have a bunch of cases. Just name them. Just give a name to them and see what the pattern is and plunge on and see what.
Hopefully, you don't run out of memory.
Well, yeah, that's right. We use in this case, it looks like there will be a subscript and a superscript. The superscript saying how many bars there are, and the subscript saying somehow where we are, how many steps we've taken from some starting configuration. Okay.
The approach that Pang and Anil and I took on Sunday was to assume that, or to try and prove that you couldn't have any processor that would swallow a baton.
You couldn't have any processor that would swallow a baton. That would go. In other words, that this would. How would it see? How would it?
Well, the idea is if you have 3 N processors and 3 2 processors or more in a cycle, you could, I guess 4 and 4.
Mm-hmm.
If you can show that no pair of N processor, 2 processor, or vice versa can swallow a baton, then you could definitely show there's a pair of batons that can travel around the ring.
Oh, so you could use the swallowing effect to construct to construct a bad cycle,
Right.
Because the swallowing would get rid of the garbage, or something like that.
Well, the sense, this came from your point last week where you said that if you had something that was recognizing a bad baton and stopping it, that then you found that it stopped the whole machine occasionally. Right.
Yeah. How does
We got stuck trying to show that you couldn't have a baton swallower.
But you do have that as a result, or that was just a conjecture.
That was a conjecture.
That was a conjecture.
And
That the baton swallower would be
solution,
enough. Yeah. Okay.
Absolutely. I wonder if anyone has tried actually constructing a sequence of, let's say, 6 processes or something.
Yeah.
I mean, let's say by exhaustive search or something like
That
that.
was my next question. Has anybody tried that?
That's what I was going to try next.
That's what you were going to try next. Okay, that's exactly what I was going to bring up next. In fact, what time is it going to be on? Okay. Let's talk about that for the next few minutes. Because I got this as far. I mean, this is the next idea I had for a theoretical approach on it. Then go to a computer and get some data. The computer will crank out a cycle, and then you say, "Oh yes, I might have been able to predict this by doing the." Okay, so let's forget this now for a time being, and go to another problem. Suppose that you were in the ACM programming contest that's I think taking place today in New Orleans with our star programmer Mike Dixon. And, is it today or tomorrow?
I'm not sure.
Yeah, I think it's one of these days. I think it's today and tomorrow. And you open up the problem, and it says, given a set of transitions corresponding to configurations that can follow other configurations in problem 4, determine whether or not it satisfies the conditions that the 5 conditions of problem 4, namely about bad configurations can't have to lead to good ones and things like that. So how would we write a program that would test this out? What would be? So you got a graph. In other words, you got a graph of you got some large number of configurations out here, and sometimes it'll have several successors. Others will have only one successor, maybe. Everybody has to have at least one successor. You could check that pretty easily. It's not a tough program to check. So how would we check to see whether a set of points and arrows between configurations satisfy these properties? Well, what are the properties one after another? Somebody have it? Yeah. So the first property was at least one processor can move any configuration. That says that there's at least one arrow coming out of every point. Okay? The next part.
When you're reading in the rules.
What?
You can determine that when you're reading in the transition.
Right. So we can read in these transitions. They're given to us as data. Let's say, and we just have this. We figure out some kind of data structure where we can at least test that everybody has at least one successor. Okay. Now, what about the next thing? At most, one processor can move in any good configuration. So that tells us then that those that have out degree 1 could possibly be good, but the others couldn't. So it gives us some handle on what might be good. There's always a possibility of something like this, where this one has only one way to go, but then this one has 3, but it'll eventually get to a good cycle. But here's a sequence of 4 things that have only one successor. We could call those good. So that's property 2. Property 3, each move from good leads to another good. No sequence of moves takes a bad into itself. Any cycle includes a move by each processor. Let's forget about property 5 for the time being and just check the other properties. So the property 5 says that if there's a cycle, each processor moves on that cycle, and we haven't, in our graph, we haven't looked at we haven't identified these moves with processors. We could put a color on each arrow or something that says which processor it is that's moving, and make sure that every cycle has all the colors. But let's forget that problem. So now, first of all, let's just check that there's no infinite bad things. What's a good algorithm for this?
Compute the transitive closure.
Compute the transitive closure. So transitive closure of a point is everything you can reach from that point.
And if you have any bad state, one where you can go 2 or more states, if you get back to itself.
Okay, so the transitive closure would be the irreflective transitive closure. So we have a rule x goes to y and we can consider that to be a relation. This is in the graph. This means the vertex x goes to y. Then the transitive closure x arrow plus y means that x can go to y in 1 or more steps. And if x plus x, then you've got a possible problem. Then x had better be good, right?
Yeah.
Okay. So you could compute the transitive closure and see, and then say that these have to all be good. For all of the ones that do this have to be good, and this would be. Then you just check to see that those have all out degree 1. Every vertex that can lead to itself must have out degree 1, and call those the good ones. Yeah?
Well, you also have to show that all bad ones filter into that.
If it's, yeah, with that, let's take that as a, suppose we just use transitive closure subroutine. Maybe it's building the hardware of our machine. A transitive closure taker. So we got a transitive closure taker, and we look at all those that can lead to themselves, and and if any of those have out degree more than 1, we say no good. Yeah.
Every time you find a bad node, find all those that point to it and mark them as bad.
Wait a minute, you're talking about another algorithm. I'm going to talk about John's algorithm first. I'll get back to you. Okay. But let's forget, so we got, first of all, this property. So we've taken a transitive closure, and we look at all those all the x for which this happens, and we know that we want all of those to have out degree 1. Now, if they all have out degree 1, we call those the good vertices, and everything else is bad. Now, is it true then that there's no cycle from a bad configuration into itself?
Yes.
Yes, because by definition, all the ones that could go into itself were declared good.
Which means that if there's a cycle
And
left,
furthermore, in any good configuration, it leads to another good configuration. Is that property true?
not yet. I mean, hold on.
Right?
Yeah.
We've defined all good configurations to be all the x for which x goes to x under the transitive closure.
Okay. Yeah.
Is it true then that every good configuration leads to another good configuration?
We've all got out degree
They
1.
all have out degree 1, and that must be part of that same cycle that goes, if x goes to x, then x's successor will go to x and then to x's successor. Okay. And then at most one processor can move that we already checked in a good configuration. So that's a working algorithm. How fast is it to take a transitive closure?
Can it be done like n squared log n now or something like that? N cubed fairly easily.
N cubed is what we would use for any n that we would ever expect to program in a finite time. Yeah, no, there are. I think it's. I think I don't remember. N cubed over log n was the bound at one time, which was based on going through log n columns at a time, but let's see. It's
Definitely,
like shortest
that's
path, and it's yeah. Wait a minute, you can do better. Yeah, because you got the matrix multiplication machinery to use now. So I think it's like the same as matrix multiplication. So it's end of the 2.49, except that it doesn't start to help you over n cubed, because the constant is so big that you have to get n more than 10 to the 100th or something before the trade-off starts to help you. But it is less than n cubed. Yeah, because I believe that's true that this for transitive closure. I don't remember now. It's embarrassing. Got to write volume 4 someday.
I'm pretty sure that's in the
I can look it up. Yeah.
It's the same number as matrix multiplication.
Yeah, I think they showed that because you can get transitive closure by multiplying matrices. You have a matrix of zeros and ones, and you multiply the matrix. Like you take a and you go to a squared, a to the 4th, a to the 8th. You keep squaring the matrix, and pretty soon after log n steps, it comes to the non-zero entries in the matrix are the elements in the transitive closure.
like n cubed fairly easily.
N cubed is what we would use for any n that we would ever expect to program in this finite time. Yeah, no, there are. I think it's. Yeah, I think I don't remember. N cubed over log n was the bound at one time, which was based on going through log n columns at a time, but let's see, it's
Definitely
like shortest
less
path,
than
and it's yeah. Wait a minute, you can do better. Yeah, because you got the matrix multiplication machinery to use now. So I think it's like the same as matrix multiplication. So it's end of the 2.49, except that it doesn't start to help you over n cubed, because the constant is so big that you have to get n more than 10 to the 100th or something before the trade-off starts to help you. But it is less than n cubed. Yeah, because I believe that's true that this for transitive closure. I don't remember now. It's embarrassing. Got to write volume 4 someday. I can look it up. Yeah.
It's the same number as matrix multiplication.
Yeah, I think they showed that because you can get transitive closure by multiplying matrices. You have a matrix of zeros and ones, and you multiply the matrix. Like you take A and you go to A squared, A to the 4th, A to the 8th. You keep squaring the matrix, and pretty soon after log n steps, it comes to the non-zero entries in the matrix are the elements in the transitive closure. Because if there's a path from x to y, there will be a path that is a simple path from x to y, one that doesn't use a cycle again, and so the maximum intermediate vertex more than once, and so therefore there would have to be a path less than n, and so the a to the n represents all the paths of length n. Let's see, that's not exactly true. You replace a by a or a squared, something like that, n times, log n times, and then you get transitive closure. So that's like matrix multiplication. Yeah, that's.
Might there be a way to do this without completely enumerating all the possible configurations? Or?
Yeah, but that's still n squared. There's a better way. N is large.
It's possible to do it much more cheaply than
Yeah, that's right. That's why I want to get. There's a faster way. So, what would you do, Ari?
Go through the notes, pick up, let's say, find the first one which you have, which has more an out degree of either 0 or, 0 obviously you already thrown away, but let's say of more than 1.
Yeah.
And find all the nodes which point to it, and recursively mark them bad.
Okay.
Of course, keeping track so that you don't go and mark a node.
Okay.
bad
So you
more than
start out
this.
with with every vertex that's got out degree more than 1, and call it bad.
And call its predecessors
And call the predecessors of any bad one bad.
and propagate backwards, remembering not to cycle back.
Any predecessor of a bad is bad. Okay. Okay. So that's that's a marking algorithm like in garbage collection or something where we have a we have a starting set, namely the ones that have out degree more than 1, and then we take all the predecessors of our set and we keep on going until we've closed the operation under taking predecessor. Okay. Now does that work? So then the ones that we weren't able to get under this operation we call good.
Yeah, subject to the condition that
So-
it changes all processes.
Well, that's property 5 we'll have to do later, but let's okay. So now does this one work? Okay. So first of all, in this case we get a different set of good ones than the other. In this example, we might get a different set of good. Well, not always not in all the examples. If we had something which every vertex has out degree 1, then in John's construction, you can suppose that take something like this. in John's construction, these would be called good, but this one not, because it can't lead to itself. But in RE's construction, everything has up. Yeah, up here?
That one has your property.
This one has this property that it's not part of the cycle, but it has out degree 1. And it doesn't have any, I don't think it'd be reached as the predecessors of the bad ones. Bad ones here are, bad guys are this and this, huh? So now let's see, what's the next property? If in a good configuration you have out degree 1, that's true because we ruled out all the ones that violated that as our first step to get. Our initial bad ones were the ones that had at least 2 moves. Every move from a good leads to a good. That was the thing that we said. That is if the predecessor. The predecessors of all our bads are bad, and therefore the successors of all our goods are good. No sequence of moves takes a bad configuration into itself. All we've done so far is classify into good and bad. So we still have to have a way of telling whether or not we lost.
It can't take it into itself because it can't lead to a bad configuration. It itself being a bad configuration.
So as we're doing this, we check that the predecessors have not already been marked. Predecessors already been marked.
If it's already been marked as bad,
then
you've got a cycle.
Is that correct? Is that true? No, doesn't work. No.
No,
Yeah,
but you can maintain
because
it
you're
as
working
how
with-
you are going back, so you can always check whether it's like.
Okay, so we started out with the bad ones and we went to their predecessors.
You can maintain a path from the bad position where you started, and always check whether you have a loop within that path.
I started at one bad position.
You started at a bad position, then you
Okay.
go back,
Yes.
maintain the list, so that when you at every point check whether it's already in that list,
Mm-hmm.
Yeah.
which means that if there's a loop you'll find it.
So there's no loops when I went back from one bad configuration. Okay, then I start with another one.
Okay.
And I start with another bad configuration, and I start going back from that. Okay. All right. There's sort of a checking for a loop-free property here. So we've classified into good and bad. I think that classification is fine. Now let's restrict the graph to the bad vertices. How do we check whether there's any cycles in that?
Check whether it's a tree.
Check whether it's a tree. How do you check that?
Depth first search.
What?
Depth first search.
Depth first search. Okay, that's one way to do it. Yeah. So, all right. No, you were supposed to take 3 more minutes to solve that because we had 4 minutes to go. Okay. Well, so that's yeah. Depth first search is a good way, probably the best. There's also like a topological sort, the same kind of a thing. You could use there's 2 competing ways to check for cycle freeness. One is the depth first search method where you keep on going down. The other one is to keep removing source vertices that have no predecessor, and put them first in an ordering, and you can complete the ordering if and only if there's no cycles. And the advantage of the depth first search one is that it gives you the cycles very directly. The other one gives it to you more indirectly. But that's, yeah. Those are so that gives a linear algorithm instead of n to the 2 plus, and therefore even Hopcroft and Ullman would believe that it's better. There's always a question on asymptotic methods as to whether or not the constants are so large that they would really apply to the problems that we're facing in a real computer program. But in this case, it's pretty clear that we got that not only is our algorithm linear, but it's very it's very linear. Hardly anything to do at each step, and would be able to grind out the answer. Okay.
Would there be any way to do this without enumerating all the possible configurations?
Because
granted, it's linear in n, but n is
n is exponential in things. Yeah, n is still though in the neighborhood of a few hundred. So in cases of interest, still that's right. Try to do it symbolically if we can. It was just trying to do here. Yeah. So the instincts are good on this. It's too bad that we haven't solved the problem, but I think we got somewhere that makes it that we don't have to be embarrassed about not solving the whole problem. Okay, so now you've got to fill out these forms, and then Thursday is the real excitement for me anyway, and I hope you have fun between now and then. One last word about this. When you're doing problems with graphics, it seems to me that sometimes mistakes are sometimes more interesting than the real thing, and I know that I often hate to throw away some of the bugs that I get because the images are kind of amusing to me anyway. If you want to bring in some of the to class on Thursday, some of the things that failed as you were developing your final project, we might all want to look at those too, although we wouldn't display those. You can just show them to people who are interested in seeing pretty postcards or something of the things of the flops, because I think graphical bugs are lots of fun. Okay, so.